Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is one MCQ about heterocyclic chemistry, and actually this is the heterocyclic nucleus. Okay, so three-step reactions is carried out on this, and you have to say what is the right answer. Four options are provided and one of them is the right answer. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. And don't worry, after some time you will get the right answer. I believe you have tried by yourself, so it's my turn to give you the right answer. And this is actually, student, the reference of this problem. Now, so if you look at this molecule, this is actually a heterocyclic moiety. Actually, this part is the heterocyclic moiety having two sulfur atoms. And first step, it is reacted with sodium borohydride and methanol. Student, if you look at this molecule little carefully, so this is carbon, this is sulfur, and this is carbon. So two types of double bond or pi bonds are there. One is this carbon-carbon pi bond and another one is this carbon-sulfur pi bond. Pi bonds are formed by the sidewise overlap of p orbitals. You may consider this is the 2p of carbon and this is the 3p of sulfur. So that's why this extent of overlap is less in case of 2p 3p, I mean this bond, 2p 3p pi bonds. Less overlap, weaker bond, or you may consider reactive bond. So that's why these will react with sodium borohydride, which is the source of hydride, which is actually a nucleophile. Okay, not only that, see, this sulfur is carrying a positive charge, means after nucleophilic attack this positive charge is going to be neutralized. What is the significance of this positive charge? The meaning of positive charge is the deficiency of electron, and we know the nucleophiles are electron rich species, so that's why this nucleophile will attack this carbon. Okay, so let's learn how it's happening. So sodium borohydride will produce this hydride and this hydride will attack here and it will open up, and the charge on this sulfur atom, means a positive charge, will be neutralized and there is the hydride addition. And so this methanol is a solvent for this sodium borohydride based reductions. Now, so this double bond is gone because it was the weakest double bond. Now you may consider that, sir, this heterocyclic moiety was having a unique stability in the form of aromaticity. What happens for that? It's true, student, but remember, aromatic stabilization is not that much high for such heterocyclic moiety. If you compare this with benzene, benzene is highly stable aromatic compound, but it is not. So you may consider a compromised situation, means it is moderately reactive. That's why this reaction happens. Now in the second step, it will react with HbF4, and we know that HbF4 is actually a non-nucleophile, means HbF4 ionizes, it produces H plus and BF4 minus, and we know this BF4 minus is actually a non-nucleophilic base, or you may consider the negative charge is on the boron atom, and boron preferred to form stable bond with fluorine, and in this case this central boron is octet filled, so it's stabilized, means you can consider this H plus is significantly stronger. So what is expected? It will be added to electron rich center. Now in this molecule, actually if you look at, there is one pi bond or alkene and 3 sulfur. We know this sulfur have 2 lone pairs of electron. I agree, student, you will say that, sir, sulfur is softer but H plus is harder, so this interaction is not that much strong. It is true, I agree with you, but there is no that much other better option also, because alkene is also a softer base. So that's why here the reaction will happen on this sulfur. So this sulfur will abstract this proton and it will be protonated. What do I mean? So you can see this is the double bond, one sulfur here, one sulfur here, this is the proton, and here this sulfur is attached to this proton. Okay, and also obviously one lone pair is left. Now this sulfur is carrying a positive charge, means it becomes a beta leaving group. How? So these lone pair on the sulfur will push. it will push here, it will come. So leaving group is neutral, that's why in this way it will produce this one. Now a simple question student may come in your mind that, sir, sometime before you told that this bond is weak, that's why it reacted with sodium borohydride. So if it is not that much stable, then how it's formed? Actually student remember that everything is dependent on the reaction condition. In this reaction condition, there was a good nucleophile, that is sodium borohydride, electron rich species. That's why it attacked this carbon. Okay, but in the next phase, only HbF4 is there, no nucleophile, because as I told, this BF4 minus is a non-nucleophilic base. So that's why this is produced. Fine. And if you look at, it's actually a salt. So and counter anion is here, this BF4 minus. But it also has this proton, and remember students, such protons are significantly acidic. Similar type of thing I guess you have observed in case of imidazolium salt. I have already discussed a dedicated lecture on this. So in this case there is also a proton, it is also significantly strong, means it could be abstracted by bases like this triethylamine. Okay, so this proton is abstracted by this, so it will come here. So in this case you can see that what is could be produced. So this is one sulfur, one is carrying positive charge and this carbon is carrying negative charge, or you may consider it's a pair of electron. There is one chance that this sulfur can take this electron back, because sometime before we showed that this pi bond is not that much stable, so one canonical form possible. So you can see this. Okay, and this is student actually a carbene. More specifically, if I say such carbenes are triplet, no, they are singlet. Okay, and this is actually the next step is student carbene dimerization process. Now you can say that, sir, in case of singlet carbene, this sp2 hybridized orbital, so this is sulfur is carrying this lone pair of electron, and there is one vacant p orbital. So how this bonding, how these two can bond and form a sigma as well as pi? How this is? Remember student, every reaction is associated with a particular extent of energy, means every chemical transformation needs some energy, and that is called energy of activation. And if that amount of energy is given, so you can expect one electron could be transferred here and it could be converted into a diradical, and these two diradical may combine and form this double bond instantly. Okay, so what are the key steps associated with this process? So the first step is nucleophilic addition reaction in terms of sodium borohydride. In the second step, protonation and carbene salt preparation. This is called student carbene salt. And third is carbene generation, because a weak base or specific proton scavenger, means triethylamine, is given, who has a lone pair of electron, and that's why it can specifically abstract proton, because this 3-ethyl group produces some bulkness such that this TEA or triethylamine cannot act as a good nucleophile. So that's why it will produce this singlet carbene, and then it will dimerize to corresponding alkene. And in this context, I request you student, please try to recall the radical coupling to get a single bond. For example, any free radical chain reaction, how the reaction ends. Actually this reaction ends by radical coupling. So please remember this step. I guess in this way it will be easier for you to understand this chemistry. Now, what is the right answer for this problem? The right answer is actually a double bond formation, but no. Why? Because no double bond here. So right answer is option A. Okay. So if this question appears in your exam less than 30 seconds, how can you solve it? First of all, you need to understand that sodium borohydride is actually a reducing agent nucleophile, and this bond is very weak. So nucleophilic attack will happen here, but throughout this reaction, student, no reducing agent is given which reduces carbon-carbon double bond. Remember, sodium borohydride reduces polar double bond. So it reduces polar double bond, but non-polar double bond could not be reduced by this reagent, and this bond is actually non-polar. Okay, so this will remain, only this will go. Now if you look at in option B, this double bond, so this is gone. This is not the right answer, gone. In the second phase, and if you look at in the second phase, that is HBF4, so in presence of this it will leave. Okay, so but with one double bond, so this is gone, this is also gone, because in the first step nucleophilic attack by hydride will happen where, so obviously there is hydride, but in the BF4 no option. Okay, so these two options gone. Now what is actually remaining is option A. So if you don't go to the third stage also, you can come up to the right answer, because these other three options are not logical based on first and second step. But student, I always suggest study completely, don't follow the tricks at the initial stage. Okay, so in conclusion, what you have learned today, that carbon sulfur double bond is relatively less stable due to improper matching of the involved p orbital. What do I mean by the statement? That here carbon having second means 2p, and this, in this case, this sulfur having 3p, so their involvement resulted in a less stable double bond, and this sulfur having positive charge is relatively more electron deficient than its neutral counterpart. It's more electron deficient because positive charge actually indicates the deficiency of electron. And remember, the spin multiplicity of carbene singlet or triplet is dependent on its adjacent atoms and lone pairs of electrons. This, it stays singlet, triplet, how it's stabilized. So that's the question. If it has a donation effect, it will be stabilized, so it will be singlet, otherwise it's triplet, means diradical. This carbene dimerization can result in carbon-carbon double bond, because two electrons, fine. And remember, carbenes are 6 electron species, so generally they are electron deficient. Ethylene substituted with 4 electrons, ethylene substituted with 4 electron rich sulfur atom may result in very much electron rich double bond, and that's why they can participate in donor acceptor complex formation with electron deficient alkenes. Like, let's see the example. So this is the alkene we produced in today's discussion, and if you look at this molecule, it is, student, a very electron deficient. Why I am saying, just look at the substituent. It has 1, 2, 3, 4 cyano are electron withdrawing, so that means you can see it's a very electron deficient, and this is electron rich. So when a rich and poor remains or stay together, what happened? Rich gives something to the poor and they both get stabilized, because it have excess electron and it has deficiency of electron. That's why you can see that their adduct, in this case their adduct, this part is carrying a radical cation, means positive charge. It has given its electron to this moiety having this radical anion, this thing. So not only that, such kind of this double bond can form, such kind of alkene can form stable bond with tetracyanoethylene. This part is not important for your exam, but for your better understanding I am saying. So it is electron rich double bond, it is electron deficient double bond, so they can form stable adduct. Okay, so this is the end of the discussion. I believe this video may be useful. If you consider my contents unworthy, then please help this channel to grow. So see you in my next video. Bye bye.